Be going through a random load cell. So here we have a HBM. It's a PWS 7 kg 05502. So 7 kg is the capacity. It has an accuracy class of 3. Max divisions 3000 max divisions. Vmin 0.001 kgs and a safe load of 10.5 kg. It does not have any load cell output on it. It is FM approved for class 1, 2, 3 groups A, B, C, D. I can't read the division number because that's blurred out. So we have an NTEP load cell. NTEP load cell, so it's been approved by the National Type Evaluation Program, and it's good to use in a legal for trade scale. It's also factory mutual approved to use in hazardous environments, and it's a 7.5 kg load cell. So this is a single point load cell. It looks like this was used in a bench scale. Because it looks like someone adjusted corners by filing down the load cell very carefully and very accurately. So this does look like a U cell that was taken out of service, perhaps to be replaced. But again, it's a random load cell, so we're going to see what we can figure out. Again, we have no data sheet on this. All we have is 4 wires, a multimeter, and a power supply. So let's take a look. We have 4 conductors, so let's figure out what excitation is. We're going to switch to resistance. Let's see, 9 times out of 10 negative excitation is black, so we'll go on to black. Red, we got about 300 ohms. Green, ooh, okay, 388 ohms. So green looks like what it's going to be. And then we have 300 ohms from there to there. So we have a green-black excitation because our highest resistance reading is between green and black. Let's just test this load cell. So black to one signal, 295. Black to another signal, 294. Green to one signal, 296. Green to another signal, 294. Okay, so we have a balanced bridge between each excitation and each signal. We have plus or minus 3 to 4 ohms. Within of each other. So yeah, this load cell ohms out good. Next step, we will apply some excitation voltage. We're going to crank up the power supply to 10 volts. There we go. Okay, so positive excitation goes to our positive power, our positive 10 volts. Negative excitation goes to our negative power. Okay. So yeah, we have excitation, 10 volts excitation applied to the load cell. We're going to switch to DC millivolts to measure the output voltage. Wait, I made a mistake. Green was our positive excitation because we had the highest resistance between black and green. Okay, so now we're going to measure our signal. So we'll just make an assumption that red is negative and white is positive. So what we have here is we have minus 44 millivolts DC. So with the load cell, no load applied, to the load cell, we should not have this high of a millivolt reading. If this was a 3 millivolt per volt load cell with 10 volts applied to it, that would mean our millivoltage with applied capacity to this load cell would be 30 millivolts. So at 7.5 kgs, we should see, with a good load cell, 30 millivolts on here. That's assuming it's a 3 millivolt per volt load cell. So let's fake a load, because we can't place a weight on here. So we are going to look at the arrow on the load cell that indicates the direction that the load cell is bending in. So we are going to bend the load cell. And we are increasing in millivolts. So we're going from negative 45 to negative 37 with some force applied to it. So this load cell has been overloaded. This cell is no good. So we were able to tell what the color code was by measuring the resistance between each of the wires. We also could tell and found out that we had a balanced bridge. So excitation was the highest resistance, signal was the second highest resistance, and between any excitation and any signal, we had plus or minus 3 to 4 ohms of each other. By knowing that, we then hooked up our 10 volt power supply to our black and green excitation and measured our signal voltage, and this load cell with nothing on it should read 0 millivolts. Right now we are measuring a permanent deformation in the load cell. This white goo covers strain gauges. Strain gauges measure the shear force and the bend in the load cell. So the cell has been permanently bent, so our strain gauges are measuring the permanent bend in this load cell. So this load cell